Welcome everybody to the fifth pitch of 2021, the event where PhD students of Politecnico di Torino can share their research with the IEEE members of our community and actually anyone else who is interested. Speakers for today will be Riccardo, Lohic, and Ethelbert. At the end of each talk, we will follow our usual pattern. There will be a Q&A session, and you can be free to write your own questions below the video in the chat, and we will provide them to the speakers. During the event, we will also post the link where you can record your attendance as a listener and get 1 hour of hard skills recognized by the doctoral school. Let's start. The first speaker for today is Riccardo Giusti from the Department of Control and Computer Engineering. He will give a speech entitled Synchromodal Logistics, Enabling Technologies and Related Projects. Riccardo is a PhD student in the Department of Control and Computer Engineering at Politecnico di Torino, working in the field of operations research. Before starting his PhD program, he worked as a research fellow in a Horizon 2020 European research project called Synchronet, developing a simulation tool to optimize freight itineraries on a graph, representing a synchromodal logistic network. Working on this project motivated him to investigate modern paradigms for long-haul transportation, especially synchromodal logistics. His research mainly focuses on designing mathematical models and implementing solution methods for synchromodal logistics, requiring decisions on different planning levels, from long-term strategic decisions to real-time replanning ones. Please, Riccardo, you can start your presentation.
Thanks for your introduction. So, as it was said, today I will talk about synchromodal logistics and also about the projects that we developed during this year of research. So, first things, I wanted to give you an overview of the contest. So we are talking about long-haul freight transportation, and we are talking about the paradigm of synchromodal logistics. So what is long-haul freight transportation? Basically, it's the movement of goods over long distances. You can think, for example, shipping around Europe or even around the world, since we are experiencing globalization since a few years. And mainly it regards the movement of goods between at least cities. So the long haul can be intended also as a long distance transportation. Usually the main transportation modes that are used to perform the shipments are the one that you can see, so trains, trucks, river barges, ships, and it's not so common, but at least it needs to be mentioned. Also, airplane shipments are performed, but usually the first four transportation modes are the most common. So to improve the quality of long-haul transportation during the year, new strategies and paradigms were coined to improve the efficiency of the networks. So we have multimodal transportation that, let's say, was the first paradigm that was coined, and involve the shipments by using more than a mode of transportation. So for instance, imagine you have to ship a container. You don't just ship that by truck or by train, but you ship that by truck, and then you move the container to a train, and then maybe you move it to a ship, depending on where it needs to go. But the main purpose of multimodality is to use more mode of transportation to perform a shipment. And then we move to intermodal transportation that try to integrate more this movement of goods between modes. And so, for instance, we're starting to develop unit load. And with unit load, we mean some type of container, pallets, or other things that contains goods that can be easily moved from a mode of transportation to another. Then there were two different focuses, let's say, starting from intermodal transportation, one that focused more on the sustainability of the operation, that it's called combined transportation. And then we have the co-modal transportation that focus more on the efficiency, so spend less. Then, let's say, all these characteristics are inherent from synchromodality, that beside that try to introduce a more sophisticated way to perform the operation. So there are some requirements that are the real-time information sharing between the stakeholders that allow to know, allow for each stakeholders to know what is going on in the relevant operation to them. And also that requires a stronger cooperation and coordination that goes, let's say, usually we have a vertical cooperation, so usually stakeholders with different businesses are cooperating, but here we need also an horizontal cooperation, so between stakeholders with similar businesses. And then both stakeholders and customers should be more flexible, both in developing the operation and also in requesting how the shipment should be performed. And that will allow to have the possibility to synchronize the operations to have more gain on doing that. So just to have a small recap, after, let's say, studying a bit what we found in literature about synchromodality, we came out with this definition that summarizes some of the characteristics, and moreover, it showed the focus that is to have an efficient in terms of cost and more reliable in terms of having services that ensure you the timing that were promised, and also the flexibility to adjust to react to disruption, and more sustainable service, so less emissions. And to doing that, a major requirement is to use new and innovative technologies. By doing that, it becomes possible to use new procedures. And so, for instance, we can have a modal booking that guarantees to a customer that his shipments are performed, and he doesn't need to care too much about the routing, the type of modes that are using. And we have also replanning. So during the operation, there is the possibility that something is planned again because something was, some disruptive event was detected. And so it needs to be replanned. And so to implement synchromodality, we found some critical success factors. And there are things going from, let's say, a legal, political perspective, something more behavioral of the stakeholders involved. Other instead are more related to technologies. And in fact, we are more interested to the critical success factor that is regarding ECT and ITS technologies. So one thing that we did was trying to summarize the enabling technologies that are required to implement synchromodality. And we did that by dividing them in different categories. So we have the traceability, that is, let's say, the capacity of being able to track the events, how the operation are performed, and so having, let's say, the real-time information needed to do everything else. Then we require the intelligent systems, both, let's say, from can be intelligent assistant that help decision maker to take decision, or even automatic machinery that help to perform the operations with a better timing. And also we require data analytics because we need more data to be analyzed, because if everything is tracked, there are data coming from object, vehicles, and everything. So that it's something that is required. And also optimization, so you're trying to improve the decisions that are taken and the utilization of the resources. And we also need simulation to try to understand how the logistics system is working, and last, integration platforms that should provide a way to perform businesses, better businesses between the stakeholders, and also have technology tools to perform their businesses. And so what we did next was to try to understand which enabling technologies could help also to succeed in dealing with the other critical success factors. And since we work in the field of optimization, we mainly focus on the enabling technologies regarding optimization, but also we did something regarding simulation and integration platform. We will then see those projects. Just to, let's say, show you the current situation of the logistic interaction between stakeholders. Basically now they are interacting with each other directly, and there are different levels, for instance, of logistics services that are offered. For instance, carriers offer single transportation services with a mode between routes, while 3PLs and 4PLs are logistics service providers that offer more complex services that sometimes also reach the supply chain management level. And instead, synchromodality would need a more intelligent communication system that offer to stakeholders to have access to services designed specifically for them that use the enabling technologies to provide those tools. So the first project I would like to talk about regards operational planning. And in operational planning, usually we are required to take decisions that affect the immediate operation that we need to do. So, for instance, assign some containers to the vehicles that will need to transport them. And right now we are doing a project with the University of Delft. It's still ongoing, and it aims to implement a simulation optimization approach on which we are simulating the logistic, the supply chain and the events that are happening to that. And instead, the optimization part should take the decision on which vehicles are shipping which goods. And if something happens in real time, some replanning procedures can be used. For instance, we can reroute the vehicles or the shipment through different itineraries, or we can reschedule them using different mode of transportation, or even adjusting the speed of the vehicles. So because, for instance, slowing down the ships and avoiding to arrive too early in a port that is congested help to avoid some emissions, because a ship that moving at less speed can have really better performance in terms of emission. And we would like to study also something related to the different type of demand that can happen, because the demand maybe can be known completely in advance, or in some case, depending on the business, can be discovered during the operation. For instance, things about Amazon that have continuously order from its customers. And also regarding the disruptions that can affect our network, we would like to study both endogenous and exogenous disruptions. That basically mean endogenous are the one that depend from us, while exogenous depends from other stakeholders that are not in our logistic networks. And also we would like to study both in case of business as usual disruption, like lateness in performing operation, or even catastrophic events like vehicle disruptions, unavailable routes, or other things. Then another project that we are working about regards strategic and tactical planning that usually involve long-term decisions that require usually huge investments and it's related to acquiring vehicles, making contracts, and other stuff like that. And we are doing a project with the University of Montreal regarding location transshipment problem, and basically a transshipment operation. It's the movement of goods from one mode to another. So for instance, from the train that you are seeing here to the trucks and so on, while the location consists in deciding which terminal we want to locate. So the facility to do the transshipment that we want to use for our business. So regarding this problem, we have already published something, and we were performing a project that was using the stochastic programming approach. That basically it's a way to take into account uncertainty. And we decided to take into account uncertainty on the handling capacity in the transshipment facilities. So we don't know exactly how much capacity will be available at the time of the operation, and on the utility that we gain from using that facilities. To try to explain it as easy as possible, you develop a mathematical model with more stage decision. In our case, we had 2, because you have to take the decision of locating the facilities long time before. So when the uncertainty is, when some information is still uncertain. And then you have to take other decisions that are how to ship things among your network that you need to take when those things are already new. And so by defining a probability distribution for the uncertainty and deriving some scenarios through a test that is called stability analysis, you can understand how many scenarios you need to have a good approximation of the uncertainty, and then you can perform other type of tests. One, it's more regarding an economical analysis of some stochastic programming indicators that can give you some indication on how addressing uncertainty is important in monetary terms, and for instance, also how being able to forecast the uncertainty can be helpful, and also give you some indication about the composition of the deterministic solution. If from the deterministic solution we can have a stochastic solution that that is better. And lastly, we develop a solution method based on called progressive edging that basically solve each scenario case one by one, and then try to converge the first stage decision to a single decision. And so we can make a comparison of the computational performance against some commercial solvers. Then the last project I would like to talk about, it's Synchronet, that was an Horizon 2020 project. And we did something that is related also to making a common platform to integrate different tools. In the project, there were involved different partners, both from academic and industrial. And so our main role was to implement the modules that you see in greens, that are basically a simulator and an optimization tool that was aiming to optimize the routing of the shipments, and could work both in a strategic tactical setting and also in a real-time settings. The platform was working in different modules. As you can see, there are different modules integrating with each others. And so, for instance, the real-time module developed from another company was communicating with our module to try to find in real time some alternative routes to replan some shipments. So I will give you a basic overview of what we developed. We make a search engine that was based on a multi-objective optimization on emission, length, and time. and it was possible to set some search options, so some basic like departure, arrival times and nodes. The user can decide which transportation modes to use, or if you want to ban or force some routes or some nodes. And it's possible also to decide multi-destination, more than a destination, and more containers for shipments. And also it's possible to configure the simulator to include the specific cost that the user known, and also to adding or updating some routes and nodes, because we were able to generate automatically some of them, but the user can also generate its own. And then this is an example of a summary. So you have information about the transportation mode. The column in colored column are our key performance indicators that can be also weighted depending on the user. And so, for instance, a user can give more importance to emission, and the results will change. And you have also other information making a summary of each itineraries. Then if you click on one itineraries, you can have exactly the information on everything regarding the specific leg of the itinerary, also regarding the boarding time, alighting time, and so on. And then the tools was tested by our industrial partners that make some tests on like number one, it was focusing on the northwest of Europe to try to understand if it was more convenient to avoid the United Kingdom after Brexit, because from Ireland they were shipping through United Kingdom, but with Brexit some problem could happen. And there was also test 2 that was the pan-European demonstrator in the Greece areas and the Balkans. And you can see how it looks to have more containers shipped with different routes. And the last one, number 3, show a shipment from China that then have more than a destination. So here you have also some reference about what we already published on our research. And I don't have time to explain all the details, but if you're interested, you can have a look at that, or you can contact me by mail and I can give you more information on all the specific project. So thanks for your for the attention.
Thank you, Riccardo. We have a few questions for you.
Okay.
Let's see. This is the first. How are the critical success factors prioritized among themselves?
Okay. Actually, I think that one, I can go back to the critical success factors. Probably the awareness and mental shift. I think it's something very important, because the first things that you need to do is to convince the people that are working in logistics to make this transition to a more collaborative system, and to show them how they can have a more efficient, sustainable way of performing their businesses. But I also believe that ECT, ITS technologies, maybe I'm talking about that because I'm working basically on that, but are very important, because with them, as I shown you before, we can try to overcome also the other critical success factor. I didn't have time to talk specifically about that, but as you can see, to create, for instance, more awareness about the importance of synchromodality, you can use some data analytics or some simulation. In the Netherlands, they were also developing some games. So they were making some people from industry playing some games regarding synchromodality. and they were making, let's say, a comparison without operating with the intermodality and then synchromodality in, let's say, a safe area that is a game. So there are really a lot of things that can be done to try to overcome all the critical success factor. But I believe probably the most important are these two.
Okay, so this, I guess this is kind of an invitation to new researchers to join you and help in your work.
Yeah, actually, as you see, both in technology, there are something that I'm not expert about, like intelligent system, data analytics, traceability, and for sure it requires some people to work about. But also in other fields require some expert to work on that. For instance, I think I am not able to work on the legal and political framework to allow synchromodality, but there are for sure more people that are expert in that field and can help. So there is basically work for everyone. I didn't say maybe that before, but this paradigm was coined only 10 years ago, and it started to be implemented mainly in the Netherlands. So it needs also to be exported to other countries and implemented, I would say everywhere, but at least in other places. So an effort from different field experts is required for sure.
I see. Since we took too long, yes. I guess I will select. No, it's fine. I hope the viewers are enjoying. I will select just one other question. Okay. Recently, blockchain technology has been associated to the management of logistics operations. In your opinion, is it actually valuable as an enabling technology in this context, or is it only a buzzword?
Okay, I haven't talked here about blockchain, but in the paper we wrote a paper about an overview of synchromodality where we talk about these enabling technologies, and we go, of course, more in details. And regarding the integration platforms, we were thinking also to use some that would be useful to use some blockchain strategy, because it seems that it can give maybe more a sense of safety to the people working there, that if their data are elaborated through blockchains, can be more safe. And also with another aspect, because blockchain sometimes was associated with the smart contracts that are basically the contracts that have some specific rule that makes something happen. For instance, you can make a contract that is a digital contract that if you are late in performing the shipment that you were supposed to do, let's say in 2 days, and you need 3 days, you automatically get fined and the money get collected. And so if you want to implement some flexible mechanism, because flexibility means also that you don't stick to the schedule, but you have policy on what to do when something wrong happens. And so also from a legal perspective, you should have some policy related to these smart contracts. And so, of course, blockchain, smart contracts, and all the things related to them can be useful in the implementation of synchromodality.
So I guess this tells that there are very practical advantages in applying blockchain and the related technology.
Yes, of course.
Okay. Thank you, Riccardo, also for this dynamic Q&A. Okay. Our second speaker, I will introduce now, is lohic fotio tiotsop from the Department of Control and Computer Engineering. He will give a speech entitled Optimizing Perceptual Quality Prediction Models for Multimedia Communication Systems. Lohic received his Master of Science degree in Mathematical Engineering from Politecnico di Torino. Since 2018, he is a PhD candidate in Control and Computer Engineering department. His primary research interests are advanced statistical methods and machine learning algorithms applied to multimedia system problems. Sorry. Please, Loic.
Yeah, so thank you for introducing me and giving me the opportunity to present my research in the context of media quality assessment. So maybe the best thing is to start with an example. And for us human, it is really easy, right, to see that the image here on the left-hand side has high quality, right? No artifacts are perceptible. While the image on the right-hand side has a very low quality. This task is easy for a human, but what about an algorithm? And since this task is typically easy for a human, originally researcher tried to use human to assess the quality of images and video. Here, by quality, I mean the perceptual quality, right? And this is known as subjective test or subjective assessment of perceptual quality. What happened? What happened is that we invite people, a number, let's say typically more than 15 viewers in a lab. We ask them, according to you, what is the quality, what is the visual quality of this image or this video? And they need to rate the visual quality using the scale that you see here. If they deem that the quality is bad, they rate it as 1, poor 2, and so on. If the quality is excellent, they give 5. At the end, to get the overall, right, the ground truth quality of the image, we take the mean of the opinion score given for each image. This means at the end of the subjective experiment or the subjective test, you get a value in the range from 1 to 5 called the MOS that represents the subjective quality of that image. Now, the MOS, that is the mean opinion score, it's reliable, being directly collected, right? Since it comes from opinions collected directly from the end users. But it has two main drawbacks. Obviously, you cannot implement the mean opinion score in real time, right? You cannot simply invite people in a system and whether they rate the quality and so on. So it is time consuming to get the MOS, and it is also expensive. Another drawback is that it does not account for individual expectations. Just think about the fact that there could be people that are really flexible and others that are really demanding in terms of quality. But the mean opinion score, being just the mean, does not give you any information about the percentage of the customer that are satisfied by the quality of the images or the video you are providing. Okay. So the first issue regarding the mean opinion score has been traditionally tackled by using what we'll see later that are called quality prediction algorithms. But the second issue is a hot topic, and I have dedicated most of my PhD research, right, to this second aspect, and we'll see later. So some words about quality prediction algorithms. They are designed for MOS prediction. And being algorithms, they are fast. Some examples are the PSNR, the SSIM, the VIF, the BRICS, and VMAF. The latter one, that is VMAF, is the algorithm that Netflix used to optimize his delivery pipeline. And in general, as you can see from the chart below, it correlates well with human perception. Now, as I said before, the second issue of the MOS is related to the fact that it doesn't account for single or for individual users' expectations in terms of quality. An example is given by this chart that represents the distribution of opinion score obtained in the context of a subjective experiment for a given video sequence. As you see, the mean opinion score of this sequence is 3.4. That is more than fair, but okay. Then, if you look at the distribution, 27% of end users are judging the quality as poor or bad. That means that 27% of your customers are not satisfied. This example shows that just looking at the mean opinion score could not be enough. So you need to compress your video sequences in order to not only have a large mean opinion score, but also make sure that the user, the diversity among user opinion is not going to be that large. The first step towards getting tools that allow to, to get also information about the diversity of viewer opinions was proposed in a journal paper, the one you see here below on the slide, in a journal paper by me and some colleagues, where I basically proposed to look at the standard deviation of observers opinion score, here abbreviated as SOS, as a measure of diversity among the user's opinion. I propose to model it as two components, a deterministic component and a stochastic one. And the deterministic component is directly related to the characteristic of the video sequence. Why the stochastic component, right? It depends on the subjective experiment setting, where you basically measure you ask the viewer to rate the quality of the video sequence. And what I have seen is that this deterministic component can be modeled as a function of quality prediction algorithms, those that we saw before. Why the stochastic component basically is normally distributed. And this model has two features. In particular, video sequences for which the sigma experiment is high are those for which the designer of the subjective experiment should pay attention about the way people rated those sequences, because there may be potential anomalies or potential inconsistency of the observers on this specific sequence. On the other hand, those for which the part of the source that is characterized by the feature of the sequence itself is high are those on which the content providers, such as Netflix and so on, or other companies, should dedicate more resources in order to make sure that there is not going to be large diversity among user opinions. Now, another step toward modeling the quality while taking into account expectation of single observer was this other proposal, in which we propose for the first time to look at the MOS, the mean opinion score, as a random variable. Why this? Because what happened is that a human observer is not able to repeat your same opinion when they are asked to rate again the perceptual quality of a video sequence they have already rated. This means that if we repeat the same experiment with the same sequences and the same person, we will get different MOS value. Therefore, we propose that for a given output of a quality prediction algorithm, we are not going to say that this corresponds to a specific value of the MOS, but rather to a range of values of the MOS. So therefore, given the value of quality prediction algorithms, we try to find the interval in which the MOS will stay with the probability 1 minus alpha, where alpha is used here as a tolerance. Now, I put here some equations to give you just the sense of what are the technical steps behind the framework. But basically, what we do is that we look at we model the joint probability distribution of the MOS and the output of quality prediction algorithm using a Gaussian mixture model. We estimate the parameter of this Gaussian mixture model by implementing a maximum likelihood model. Later, once we get this joint probability distribution, we figure out what is the conditional probability distribution of the MOS given the output of quality prediction algorithms. And then we simply took the quantile at alpha over 2 and the 1 minus alpha over 2 to get the boundary, right, of that interval. And the main results coming from this framework were summarized and published in this work that you see here below. Okay. Now, at a certain point in my research, I asked myself, okay, why people are still insisting in trying to predict the mean opinion score, while we know that it doesn't account for individual observers' expectation. And therefore, I propose a new way to think about on how to automatically measure the quality. And in particular, I suggest two trends neural network that can be used to mimic actual observers in terms of quality perception. Let us be more precise. Let's suppose that I invite an observer called Peter in a subjective experiment. He rates some video sequences, And then I use the Peter ratings to train a neural network that can then substitute Peters in terms of quality perception. And this neural network will be called artificial intelligence-based observers, or Peter, or the Peters AI observer. Now, we do this for Peter, but we can do it for Alice or many other observers. And once you get this AI observer, and suppose the guy that is in charge of compressing the content at Netflix wants to rate the quality of a new video sequence, what he can simply do is to use the AI observer to get a large number of opinions, and he can then draw the distribution of opinions from which he can compute not only the mean opinion score that he will have got by using VMAF, but he will got not only the mean opinion score, but the percentage of users that are not satisfied, and also what are the characteristics of these users that are not satisfied. This information are really as crucial importance for optimizing the overall policy of a company, right? So to train the AI observers, those neural networks that mimic the quality perception of individual observer, we adopted two main approaches. The first approach is by using small-scale neural networks that are less data demanding. And this approach consists of taking an image or a video, extract some characteristic or feature of the image, and then regress them to the quality scale. This approach was the most natural one because, unfortunately, the media quality assessment community really lack a large-scale data set that are important for training deep neural networks. In order to switch to deep neural networks, we needed a trick. And what is that trick that we proposed? Our trick was as follows. We proposed to the community to use synthetic data for computing a first training stage, and then using what is known in the machine learning community as transfer learning to yield deep neural network-based AI observer. And our synthetic data set was generated by taking one image and compressing it with 5 different levels of JPEG compression, and labeling this different level of JPEG compression as bad, poor, and still excellent. Then we use this large-scale synthetically created data set to train a deep neural network called JPEG ResNet with up to 50 convolutional layers, right? And once this neural network, at the end, it's able to classify the images in terms of JPEG compression. That means that it's a neural network that has learned what are important features for judging, for modeling perceptual quality. Then we take this neural network, we combine it with the data given by an observer, let's say, for instance, Alice, during a subjective experiment, and we perform a transfer learning step during which the feature learned by the JPEG ResNet 50 are progressively transformed into new features that characterize the Alice perception of quality, yielding the deep neural network-based AI observer of Alice that is a neural network with the same structure as that of the JPEG ResNet 50. Now, let us summarize some main results about these AI observers. And in particular, we have seen that just like humans that are really good in evaluating bad quality and excellent quality, the AI observer do the same. Okay, and some other aspects, some other advantage of this approach is that, as I said before, observers are not able to repeat the opinion, right? When they are asked to rate again the quality of an image or a video that they has already rated. But when it comes when we use this approach, we have the way to measure, okay, the repeatability or how consistent will be an observer regarding its perception of quality for a given video sequence. In terms of accuracy, in general, what is known by empirically is that if we ask users to rate again sequences that they have already rated, they have an accuracy of 50. They will repeat the same exact first opinion just on 57% of the sequences. But what happened for the AI observer is that the percentage that we observe for the AI observer are really close to this benchmark. And we did the experiment on 3 data sets. And as you have seen here, the values that we obtained are really close to this benchmark. Also, something that we have observed regarding the AI observer is that the mean opinion score of the AI observer correlate well with the mean opinion score of actual observers. So if you want, this means that the AI observer are a good proxy for also estimating the mean opinion score. But they do more than that. Another example is that after training our AI observer, we gave them these two images. The one on top, it's obviously of bad quality, and to the right, you see the distribution of the opinion score of the AI observer. That, as expected, it's fully concentrated on bad and poor. Why? When we give an image with a better quality, the distribution, this is the distribution of opinion that we obtain, okay? Where just few persons deem the quality as bad, few AI observers, right, deem the quality as bad, and the other deem it at least fair. Okay, so here are some references containing some of our published work on the AI observer, 2 journals paper and a conference paper. This last one is still submitted, but if you are interested in having a look on that, I will be super happy to share it with you. And yeah, that's all. Thank you for your attention, and I'm here for your questions.
Okay, thank you, Loic, for your presentation. We have indeed a few questions for you.
Okay.
Okay. In one of the first slides, you have shown that there was a parameter alpha. Okay. The first question asks, what are the parameters that determine the alpha threshold that you showed?
Sorry, let me go back to this one, probably. Yeah. Okay. So basically what we are doing here is that given we want to find an interval in which the mean opinion score stay with a certain probability. Okay. Let's say I want to find the interval in which the mean opinion score stay with the probability of 95%. Then alpha is going to be 0.05. So it is something that the user of the framework decide himself. Okay. That's the point.
Okay. Okay, thank you. The second question asks how much it costs more in terms of resources and decision time when you use deep learning based solutions as compared to other statistical solutions.
Yeah, that is a nice question. I mean, at the end, it's known that a deep neural network takes time to be trained, but once they are trained, okay, they could be used efficiently. So the part that is time demanding is the training process. And for instance, the JPEG ResNet and the AI observer and the deep neural network based AI observer that I have been talking about here took us like more than 1 week for training. But when it comes to use them to evaluate the quality of an image, it takes few seconds. So summarizing, in general, you lose time just during the training phase, but during the evaluation phase, they are as efficient. In general, they are as efficient as statistical of base models.
Okay. Next question is, while the perception of images can be controlled during the tests, how can you know how people really perceive the images on different devices and technologies?
Yeah. In fact, I mean, here I gave you, just an overview, because subjective experiments involve a lot of parameters, okay? And there have been a lot of work and lot of research about how to conduct such subjective experiments. And this parameter need to be taken into account. For instance, there are ITU recommendation on what should be the size of the screen. If you do the experiment using this device rather than this one, how should you interpret the results? And there are also some quality prediction algorithms that takes into account that are specific, let's say like this, for certain devices. To give you an idea, we had during the last year a collaboration with a large media company where they have a specific model for streaming for video that they stream on demand for that you see on your TV. While they have another model for videos that for let's say for mobile applications and so on. So it is a really nice question, and the short answer is we can objectively take into account this parameter when designing quality prediction algorithm as well as when projecting subjective tests.
Okay, and the last question, I think it completes the previous one. It says, is there a way to transfer what you learn offline to real user experience?
I mean, what you mean here, just to make sure that I got the question, during the learning process, we are just trying to mimic, right, the perception of the quality perception of viewer that we were able to invite in a subjective test. If the question is, okay, can we use this model that we train for those specific observers that attend to our experiment to generalize or to measure the perception of other users? In general, speaking in terms of average, yes, but we basically opt that when designing the experiment, you select your viewers in such a way that they are representative of the overall of the whole population, right? And these subjective experiments are designed in such a way that you select the samples of viewer based on characteristics such as the age, the experience, the background. So in the end, what we learned, we hopefully should be able, at least one of the AI observer, to be representative of any other a cluster of other observer in the world population. I mean, I hope this is the good interpretation of the question.
I mean, even if the person who asked is interested, he can get back to you, I guess.
Okay. I hope so.
Okay. So thank you, Loic.
You're welcome.
We will go on with our third and last speaker, who is Ethelbert Zemobi from the Department of Aerospace and Mechanical Engineering. He will give us a speech entitled Prevention of Thermal Runaway through Accurate SOH Estimation with Parallel Layer Extreme Learning Machine. Ethelbert received his bachelor degree in mechanical engineering from the Federal University of Technology in Owerri, Nigeria, in 2010, and a master's degree in mechatronics engineering at Politecnico di Torino. He is a PhD candidate at the Department of Mechanical and Aerospace Engineering at Politecnico, with ongoing research circled around artificial intelligence and energy management applications in automotive. As part of his program, he is currently serving as a visiting researcher at the Department of Mechanical and Mechatronics Engineering in University of Waterloo, Canada. And if I can add, he is also one of us. He is also part of the IEEE student branch organization committee, let's say. So thank you, Ethelbert, for your service, and we will enjoy your talk now.
Thank you very much for that introduction. Thank you also, viewers. I will be talking, as has been described, on prevention of thermal runaway through accurate state of health estimation with parallel layer extreme learning machine. I'll try to make this presentation very simple so that it will be relevant for both the specialist and non-specialist audience, which I perceive we have here. Let's start by giving some motivations why we want to do this work. In the recent years, EU has been very, very strategic.
I'm sorry, Ethelbert. I'm not sure whether you want to share something or not, because we are not seeing.
I am sharing my screen. Can you see my screen?
Not yet.
I'm sharing already. Okay. Okay. Can you see it now?
Yeah, I guess Yuri behind the scenes is managing it. Okay.
Can you see my screen?
Yes. Can you share the slides, actually?
Okay.
Okay. Perfect. Thank you.
Oh, sorry about that.
Oh, we lost it again.
You lost it?
Yeah.
I don't know what the problem is, really. I go back. Let me know if you can see it.
We see your desktop. I mean, I see your desktop. Can you put the slides on so we can
Oh, yeah,
put them
sure.
in the live? Okay. Okay.
Is it okay?
Yep.
Oh, yeah. Thank you very much, and sorry for
Yeah, no worries.
interruption. So let's start by giving some motivation why we're having this discussion. In the recent year, EU has been very strategic in policy implementations to reach the goal of climate neutrality by 2050, as been proposed by EU and other major stakeholders. And interestingly, the idea is to continuously replace the billions of existing internal combustion engine vehicles, which contribute to about 87% of the global petroleum consumption and about 33% of the global energy. So replacing these, I think, will have a great impact in reaching that goal. Interestingly, the sales of electric vehicles from 2010 to 2019, as can be seen here, has been quite promising. And this reinforces the hope of reaching that goal. The truth is that no mission is said to be successful without stories of failures and pain points, and this isn't going to be an exception. Just in 2018, more than 16 cases of incidents are recorded, and these incidents are fire incidents associated with electric and hybrid vehicles. And you can agree with me that this scene is quite unpleasant. We don't want this. But sadly, this threat will continue to grow with increasing the demand of electric and hybrid vehicles, and as the need to increase the energy and the power density of the cells will grow. What is the problem? The root cause of this whole fire incident is the terminology, the phenomenon known as the thermal runaway. Normally, the battery is designed to work within state of charge or state level between 20% to 80%. Outside this zone, an uncontrolled application of the battery is very, very unsafe because of the rapid change in the voltage around that, outside that zone. Also, the temperature of the battery is increased with the current demand, current request in cells. As can be seen in this plot, with 7C being the highest current and 1C being the lowest current applied or requested from the battery. And there are high peak currents that are associated with electric and hybrid vehicles. These high peak currents set conditions in the cells, that drives the cell cumulatively with the condition on which the battery is being operated to a third level degradation of the battery. And at this point, the thermal runaway is inevitable. And usually the battery is set on fire. Now, let's dive into the details to understand what we need to do to solve this kind of problem. We'll talk about the state of health and how we can estimate it and what use it is for us. What you see here is a cylindrical cell that is usually common with many hybrid electric vehicle and electric vehicles. In every cell, you figure out that usually with aging of the battery, the inactive area tends to grow. This inactive area has to be monitored properly if you really want to know the actual state of charge of the battery. Because if it's not known, you have a fake information about the state of charge. Remember that you want to ensure that the battery is operated within the required zone of 20% to 80% state of charge. So accurate state of health estimation is very crucial for this. That's not all. The second problem is that the aging characteristics of the cells that have the same specification varies. It's not the same, even if they are subjected to the same load condition. This is simply because currently the chemical industry is not able to guarantee determinism in the chemical processes, especially in the lithium-ion cells. By the way, I would like to point out that I'm going to use cell and battery interchangeably. Where I need to talk about the group of cells or group of batteries, I will be specific with the term battery pack. The cell you see by the plot you see at the lower right is the degradation pattern of cells, 4 different cells of the same specification, 2 ampere hour capacity lithium ion cells. And you can see that although these cells have the same specification and they are subject to the same load condition, yet the pattern of change of aging changes, over time. And this is really something that an algorithm that is chosen to estimate the state of health has to take care of. It has to be able to adapt to this change and still be able to accurately measure state of health in order to correctly predict the state of charge. And in a typical electric vehicle, we have hundreds and thousands of these cells put together. You can see how crucial it is that this algorithm has to be as adaptive as possible. Now, let's talk about the algorithm that we are going to present in this work. This is a parallel extreme learning machine. It's a parallel layer extreme learning machine, sorry. This is a tool that became a solution to, for me, a possible way of solving this kind of problem. Usually is with transfer learning, because these batteries, their behaviors are quite large. So you want to find a way to adapt the behavior of one battery to another. Usually this is solved with transfer learning. But this algorithm, as simple as it is still able to solve this problem. The building block of the PL-ELM is the ELM proper, that is the extreme learning machine. Each of the blocks you can see here, block 1 and 2 are the blocks of extreme learning machines, which is just a single layer feed-forward neural network. Now, when they combine together in this parallel mode, they build a stronger structure. The structure of this PLM is composed of the input layer, the hidden layer, and the output layer. The input to the model, to the architecture, is the feature variables that are believed to characterize the state of health which we are about to measure. So the inputs we're going to discuss in the following slides. It combines with the weights and biases. And these weights and biases are assigned deterministically, and they both pass through a nonlinear activation function. Here we use a sigmoid function, and this gives us a hidden layer matrix of H. Also, the same happens for the second block, second ELM, and then we combine 2 of them with element products of the 2 of the matrices to get H, which is the hidden layer matrix. We know the Y, which is the state of health which we intend to estimate, or the one we have, the measured state of health. Now, the only unknown is the output layer matrix, output layer weight, which is theta. And this theta is computed simply by the generalized Monpenrose inverse matrix of the hidden layer matrix H times the output measurement, which is Y. And once we have these output layer metrics defined, we're able to multiply it with the hidden layer metrics, which we already set with the deterministic weights and biases, and we can estimate the state of health here. So that's so simple. You know, the capacity, the nonlinear handling capacity of this model is associated with the fact that these two non-linearly activated blocks combine in a way that it's projected in the feature space to handle the problem in the most efficient way than a single ELM model will do. Now let's talk about the feature extractions. As you know that the features are the inputs of the structure of that PL-ELM structure, and they are used for the training of the model. We have the privilege to have our data collection from the Prognostic Center of Excellence at NASA, and we use these data sets to train our model. The figure you see here on 1A is the characterization of state of health, and the features for this characterization are voltage, the state of charge, and the energy in watt-hour. You can see how the state of health changes in this arrow. So the aging is in the direction of the reverse arrow. The features are extracted by discrete variations of the state of charge, the voltage, and that of the energy. These things are put within, these features are put within, they are captured within a buffer of 90 seconds. Of course, it's variable, but we have chosen 90 seconds time length of buffer for the best computation. And you can see here that the result is quite nice with a root mean square error of 0.046. We also show, and this is actually in the training phase, we show the error distributed within 99% confidence level. And you can see here that all the errors lie within minus to plus 0.15. Then again, I forgot to mention that the structure of this algorithm is selected by varying the number of neurons. By varying the number, you can choose the more reliable, the more accurate model as you desire. So you can see from here, the 2C, that the model reached a stability at around 10. So, but we used only 12 neurons for designing our model. Now, in the prediction, since we have our model ready, the next is for us to use the model to predict the state of health on other batteries. So we used only one battery, which is battery number 7, to train the model. And now we use other batteries to validate it, the battery number 5, 6, and 18 to validate our model. And as it can be seen here, the model has shown to be very, very adaptable to the whole dynamics and predict the state of health very accurately for the rest of the batteries. And here we can see that the root mean square value is quite nice. I think the maximum there is 0.73. And we also have, you can see the error bound is quite little too. That's for the worst case scenario, we have between -62 to 1.31. Then a bit of comparison with just a single layer feed-forward neural network, which is the ELM, as I discussed earlier. You can see that this ELM doesn't have as much capacity, as much capability as in adapting to estimate to the changes in the state of health, and that gives us a lot of errors in prediction. watch that number B, watch the figure number B there, and you figure out that the error bound is quite large, from 3.18 to 4.82, and the root mean square value of 1.563. Yeah, you know, one interesting thing about this PL-ELM is that it actually, with a less model complexity, it's able to give a more accurate model results than ordinary ELM. I can tell you that with experience and with experiments, that even by increasing the complexity of the model for the ELM, we're not able to get a better result. So some benefits of this PL-ELM are quite simple, because you can see apparently what we do is just a least square to obtain the output metrics. Quite simple, and very, very fast, very, very computational efficient. At the end of that, when the model is trained, of course, also very fast. We can predict state of health just in 93 microseconds. That's super nice, and that's why it's very suitable for online application, considering also the minimum space that it takes in the memory. Let's move on. So without letting you get lost in so much of the details, I would want to summarize this work and with a bigger picture, so that we can understand what we want to achieve here. The goal is for us to measure state of charge accurately. And for us to do that, we will apply the model we have discussed in this work to predict state of health, even for different cells that exist. When we are able to predict the state of health, we use it to correct the state of charge. And if we can correct the state of charge and get the precise state of charge, we also need an information about the thermal condition of the battery. We use other algorithms that we developed also in the lab to predict the state of the temperature of the battery. And when these two algorithms are put together, they are all buckled into the BMS, the battery management system. And with that, you can guarantee a safe operation of the battery pack, of the entire battery pack. And this is what we want to achieve. Without using this model, we have a very high risk, potentially dangerous situation, because you can see that the risk impact with where the battery, the thermal abuse and the electric abuse is so high. And this is more reason why we have thermal runaway. But by controlling these appropriately, by accurately measuring the state of charge and using it, state of health, and using it to correct the state of health, we can move the electrical abuse from the state of the dangerous state to a relatively safe zone. The same also apply for the thermal abuse. And when we do this, we can enhance the safety in the use of our electric and hybrid vehicles, and also achieve the goals of EU and other major stakeholders of reaching climate neutrality by 2050. These are some of the work that we have published that may be relevant for you. If you might want to search on them, you can get them and download them and read them for more details. Yeah, they told me that working in the batteries are quite boring. I hope I didn't bore you, but really it saves life. So that's why we're doing it. Thank you very much for your audience. Thank you.
Thank you, Ethelbert. I mean, I guess it requires a lot of work to give a reliable estimation, and even if we don't perceive it in our daily life, I guess any electronic and any electric power device now needs this kind of work. So thanks a lot.
Thank you.
We have a few questions. Let's see. Apart from state of health, what are the other parameters which can be a good measure for the health of a battery?
Okay,
Do you have
for
any
the what?
alternatives? Apart from the state of health, as you described it, are there any other parameters that can be relevant metrics to characterize?
Okay, the health of the battery. Yes. Actually, there are different metrics that exist for measuring the battery aging. Yeah, some people just use capacity, of course. Yeah, and yeah, a couple of them out there in the literature, but the most pervasive, I would say, is the state of health. Of course, I don't know if it has been properly adopted, and but most people use it. Yeah.
Okay, I see. And finally, how would the algorithm you propose work in a practical application, and what are the limitations?
Okay, yeah. One, as how it can work in the application. Usually, what we experience is that in the charging phase of the battery, we can use like a constant current load, as can be seen that the experiment is conducted here with the constant current load condition. If this is the case, we can accurately estimate the state of health on the go. Yeah. What we do actually is we when this algorithm is put in the BMS at that time slot of 90 seconds, which is the buffer length, we capture a discrete value of the feature variables, which we feed in an installed algorithm that has been trained, and with this, state of health is estimated online. So that's how it works. Then as for the limitation, this algorithm has not, like I said, it works very well if you just want to use it at the charging phase, which is quite common with electric vehicles that charge, that they just have to park the car and then they charge. But with dynamic profile, it's a bit difficult to estimate the state of health with this. We're still trying the classification algorithm that exploits also ELM because of the elegance and computational efficiency. So yeah, that's one of the limitations. The limitation is that it hasn't been proven so well for the dynamic load, but for the constant load, very, very fine. Thank you.
Okay, thanks for the very complete answer. I guess this ends the active part from the speakers. We will now, as usual, provide a virtual certificate to the speakers that very kindly accepted to share their work with us today. You can turn your okay, I see you. For the time being, it's only a virtual certificate. We are getting closer to the normality, so we will, in the near future, organize some physical event so that we can be together once more, and also provide you with our awesome t-shirts. Okay, so let's start with Riccardo. I guess we will see live. Yes.
Thank you.
Yes, for you. Okay, then Lohic, please. A certificate for you.
Yeah. Thank you so much.
And finally, Ethelbert.
Thank you so much.
Thanks a lot, guys, for all your effort. This concludes this event. I'm not sure whether we will meet again before the summer break. I hope so. I also hope that our viewers were interested in understanding and having an introduction to these very active and relevant fields. Thank you again to the viewers and the speakers, and see you soon.
Thank you.
Bye.
Bye.